within chapter 5, the first idea that we talked about was a probability distribution. Remember, we said that was a distribution for values of a variable where how often the values occurred was represented as probabilities. Or we could represent that with a table of 2 columns. We can also represent it as a graph where the variable is on the x-axis and the probability of each variable is on the y-axis. So it's a probability distribution. And then we talked about a binomial probability just now. So now the next concept we're going to talk about is going to merge these ideas. So the third concept we'll talk about is a binomial probability distribution. So a binomial probability distribution is when you have a probability distribution, like this table with the x and p of x's, but all the probabilities in this probability distribution end up being binomial probabilities. So this is a special case of a probability distribution, where if you have a probability distribution and all these probabilities in the probability distribution are binomial probabilities, then that's a binomial probability distribution. So let's look at an example. So again, I should just draw this picture down here. So this is just a general, generic probability distribution where the probabilities can be anything. And in the special case of a binomial probability distribution, all the probabilities are coming from the binomial probability form. Okay, so let's talk about an example of this. Okay, so let's say that you have a coin that is fair. And so let's say that you flip a fair coin ten times. So the first thing we'll do is, let's say I asked you to construct a probability distribution that represents the number of heads that you observe every time you flip a coin 10 times. So construct a probability distribution representing the number of heads observed out of the 10 flips. So a probability distribution is just all values of a certain variable. Here that variable represents the number of heads observed out of 10 flips. And then the second column is each probability. So that'll be this. So the variable x here represents this quantity, the number of heads observed out of 10 flips, and then we have the second column p of x. And then for any distribution, we want to list out all possible values of this variable. So this variable represents the number of heads observed out of 10 flips. What are all the possible values? 0 through 10, excellent. You can't get a negative number of heads observed. You can't get more than 10 heads observed out of only 10 flips. So it's 0 through 10. So then, how do you find each of these probabilities? For example, if you wanted the probability of 3 heads out of 10 flips. Yeah, so 1/2 raised to the third power. This is saying that you want 3 heads out of 10 flips. Are we done? Well, you know there has to be another component, because if you want 3 heads out of 10 flips, that means you must have how many tails out of 10 flips? That means you must have 7 tails. So now you have to multiply by the probability of tails. And the probability of getting 1 tail is 1/2, and then multiply by itself 7 times. Are we done? Okay, what else? Yeah, there's a counting component, very good, because this implies that you want the probability of only the first 3 flips to be heads and the remaining 7 to be tails in exactly that sequence. But we know that this means that you want the probability of any 3 of the flips to be heads, and not just the first 3 flips. So now there's a counting component where you have to consider all the possible ways to get 3 heads out of 10 flips. So that's going to be 10 choose 3. And this represents the probability of any 3 of the 10 flips being heads. And how would you find the remaining probabilities? Exactly the same way. So all these would then be binomial probabilities. But let's practice on one of them in particular. Let's do 0 heads. That means that they're all tails. So if you want the probability of 0 heads, we're going to use the same binomial probability formula. It'll be what choose what?
10 choose 0.
Yeah, 10 choose 0. And then let's expand it out before we start evaluating. Times the probability of success or heads for a fair coin is 1/2. Raise the number of heads that we want. Yeah, in this case it's 0 heads. Times the probability of tails for a fair coin is 1/2. Raise the number of tails we want, which is 10. Okay, so this is technically the full expression, but we can simplify this a lot. It turns out that 1/2 raised to the 0 is what? Is 1. Anything to the 0 power, besides 0 to the 0, is going to be 1. And then 10 choose 0, what do you think that is? Yeah, so go ahead and maybe try to punch it in.
1.
Yeah, you get 1. And so anything choose 0 is actually defined to be 1. And one of the reasons for that is, remember, choose, that operation means that, for example, if you had 10 choose 2, what that means is how many groups of 2 things can you have from 10 where the order of those 2 things doesn't matter. That's what 10 choose 2 means. But 10 choose 0 means how many ways are there to select 0 things from 10. And technically there's only one way to do that, which is not to not do anything. So there's one way to choose 0 things from 10, which is to not do anything. So technically this is 1. So this, you have 1 being multiplied by 1, being multiplied by 1/2 to the 10 power. So this simplifies to simply 1/2 to the 10 power. So that originally, when you had these 3 components in this binomial probability, it reduces down to simply 1 component. And this should seem kind of familiar, because you're able to answer this question of what's the probability of flipping a coin 10 times and getting all tails and getting no heads. You're able to answer this without knowing what a binomial probability was in the past. Before, you simply used the multiplication rule and said probability of the first flip is tails, is 1/2. And the probability of the second flip is tails, is another 1/2. And you multiply all those 1/2s together, and that's why you got this final answer, 1/2 to the 10. But the point is that you can get the same answer using the binomial probability. And the multiplication rule that you used in the past is really just a special case of this. Okay, any questions? Okay, so the point is that in this probability distribution, all these probabilities representing the number of heads that you could observe, these are all binomial probabilities. And because all these probabilities are binomial, this is a special kind of probability distribution that we call a binomial probability distribution. Because all these probabilities are binomial. Any questions so far? Yeah.
For all of this stuff, are we gonna figure out that, or are we gonna be given a chart that looks like that?
So really you should be comfortable with each step here. So if I ask you to construct a probability distribution, you should be comfortable with generating this distribution to begin with. And then once you generate it, if I ask you, is this a binomial probability distribution, you should be comfortable saying yes, because all these probabilities end up coming from the binomial probability formula. So this whole distribution, this whole probability distribution is a binomial probability distribution, because all of these probabilities are binomial probabilities.
And then once you get to 50% of your distribution, the other 50% is basically the same.
Yeah, excellent.
Correct.
Because then you can recognize, because of what we said before, each of these these chooses is symmetric. So 10 choose 5, for example, is the same as 10 choose 5, and then 10 choose 4 is the same as 10 choose 6, and so forth, because of what we said earlier. And so half of these probabilities are going to be exactly the same as the other half. Very good observation. Okay, so, and that's something that we'll revisit in a little bit. So, now that we established that this is a binomial probability distribution, because all these probabilities are binomial, now let's talk about finding the mean. So, anytime you have a collection of numbers, we're interested in finding the mean and the standard deviation. So, let's find the mean of this binomial probability distribution. So before we actually calculate the numbers, let's talk about intuitively what you would expect the mean to be. So what it means to be the mean of this situation is every time you flip the coin 10 times, let's say that you observe how many heads you just saw. So let's say that, so this will be the number of heads from 10 flips. So let's say the first time you flip the coin 10 times, you observe the number of heads, and let's say you see that you have 6 heads. And the next time you flip the coin 10 times, you see you have 4 heads. The next time you flip the coin 10 times, you have 5 heads. The next time you flip the coin 10 times, let's say you have 7 heads, and so on. Well, let's say that you repeat this process a number of times that approaches infinity. So you flip this coin 10 times, 1,000,000,000,000 times. So you do 1,000,000,000,000 experiments where each experiment is flipping the coin 10 times and observing the number of heads. So if you take the average of all these, what do you think the average should be?
5.
Yeah, so why do you say that?
Because one is like directly in the middle, and if you look, the counting is it's the bell curve. If you look at the graph, because when you get to like 3, it'll counteract what 7 was, since you're flipping the order. Like,
Yeah, good. So another way to say that is that because this coin is fair, if you flip it if you flip it 10 times for a small number of experiments, then on average you might not get exactly 5 heads. But if you repeat this experiment a number of times that approaches infinity, like 1,000,000,000,000 times, then if you take the average, you're going to get 5 heads. So because you're only flipping the coin 10 times for each experiment, so if the coin is fair, then it should be 50% of the 10 flips being heads, which is 5. So the mean, you should expect, in this case, to be 50% of the 10, which is 5. But remember, in the past, we talked about if you have any probability distribution, we talked about finding the mean. And do you recall how to find the mean for an arbitrary probability distribution in general? So we said that you could enter these two columns in your calculator, it'll give you the mean. But how else could you do it if you were to do it by hand? Yeah.
Multiply the x-type frequencies and then divide by the number of frequencies.
Add them all up and then divide by the number of frequencies. Very good. So that would involve here multiplying each x by each p of x, and then dividing by the sum of all the p of x's. But you know that in a probability distribution, all the p of x's add up to 1, so divided by 1 doesn't change anything. So really, in a probability distribution, the mean is just adding up the product of all the rows. So multiply the rows together and just add everything up. So in this case, you could do the same thing to find the mean. You could multiply 0 times this probability, plus 1 times its probability, plus 2 times its probability, and so forth, all the way until you get to 10 times its probability.
Wouldn't we only have to do it halfway and then?
Yeah, if you recognize that this is symmetric, you could only do half and just multiply by 2. But let's say that you didn't have that insight, and you added all these up. The problem with that is that each of these individual probabilities comes from a long formula. And it's very tedious to find each of these probabilities using the binomial probability formula. So it turns out that if you're to do that, you get exactly the answer 5. But this 5, you notice that we were able to come up with it very quickly without having to do all that. So it turns out that if you have this special case where you have a probability distribution and all the probabilities are binomial probabilities, i.e., if you have a binomial probability distribution, then finding the mean is very easy. There's a shortcut that you can use, and what do you think the shortcut is, based on what we talked about? So if you have this, if each of these probabilities are the probability of a number of successes out of n trials, and p is the probability of success per trial, like for a fair coin, the probability of heads is 0.5, then how do you think we can quickly find the mean?
It's the median, right?
What is it?
It's the median, right?
Yeah, and how do we quickly find the median?
What?
Well, in this case, coincidentally, it was the median because it was a fair coin, and it was 0.5, and we're trying to find 0.5 or half of the number of trials, or 10, so half of 10 ended up being 5. But this probability isn't always going to be 1/2. So how do you think we can generalize this? Yeah, so it turned out to be 1/2 times 10, that's how we got the 5. So we simply multiply the probability of success, which is 1/2, and we multiply that by our n, which is the number of trials. So the shortcut then for finding the mean is simply to take n times p. So n is the number of trials, in this case 10, and p is the probability of success per trial, or the probability of heads, that was 1/2. And in this case, it was 10 times 1/2, and that's how we get the 5. Any questions? So, we're going to use this symbol for population mean. For any binomial probability distribution, the mean is going to be n times p. So now let's also talk about the standard deviation. In the past, for a general probability distribution, there's a formula that we talked about to find the standard deviation. It's a relatively complicated formula. And to remind you, we said the formula was the square root of the average square distance from the mean And to find the squared distance from the mean for each data point, we take x minus the mean and square it. This is the square distance for each value x, but if we want to find the average square distance, we add these all up, but then we weight it by the probability of each x. So this ends up being the formula for finding the standard deviation for any general probability distribution, which we talked about last class. But if we do that for this binomial probability distribution, that's very complicated to use that formula. But it turns out that there's a shortcut. If specifically that probability distribution is a binomial probability distribution, then the shortcut is to use this formula, the square root of npq, where q is defined as the complement of p, or 1 minus p. So let's apply it to this example. Let's find the standard deviation using the shortcut formula. So in this case, what's n? Yeah, n is the number of trials for each binomial probability. So in each binomial probability, we're finding the probability of a number of heads out of 10 flips. So n is 10. P is the probability of success per trial. Yeah, for a fair coin, in this case, it's gonna be 1/2. And then Q is the probability of non-success for each flip. And non-success here is getting not heads, but tails. So probability of tails for a fair coin is also 1/2. So go ahead and punch this in and let us know what you get for the standard deviation. Yeah, 1.58. But just so that we can see the big picture, let's take the standard deviation of 1.58 and let me say that I'll approximate it to 1.5. So let's say that I approximate the standard deviation as 1.5. And you'll see why I'm wrong. So now that we have the mean and the standard deviation of this distribution that represents the number of heads that we observe, if we flip a fair coin 10 times, the mean is 5, and the standard deviation is 1.5. So let's talk about the meaning of those numbers. So if I ask you for this situation of flipping a fair coin 10 times, if I ask you what is the most typical number of heads that you should expect to observe if you flip a coin 10 times? So you flip a fair coin 10 times, and you might observe a different number of heads each time, but what is the most typical number of heads that you should expect to observe from flipping a fair coin 10 times? Yeah, it's 5, very good. So it's 5, and so another way of asking this question is what is the mean of the number of heads observed from flipping a coin 10 times? So this most typical number, another way of saying that is the mean. Or the symbol mu that we talked about. And in this example, that mean or most typical number is 5. And so the second related question is, this most typical number being 5 heads that you observe, does that mean that you're going to observe 5 heads every single time that you flip a coin 10 times? No. So that leads into this next question, which is, what is the typical range for the number of numbers that you observe representing the number of heads out of 10 flips? So what is the typical range of values representing the number of heads observed from flipping a coin 10 times? Okay, so let's talk more about how we can answer this question. So now we want to find this typical range of values. So every single time we flip this fair coin 10 times, we want to know if the coin is actually fair, what's the range of values we should expect for the number of heads from these 10 flips. And so in statistics, when we say the values are typical, what we mean by that is we can quantify it with 95% within the mean. So for any distribution, let's say that this is the mean. All the values that comprise 95% of the values around the mean, we define as being typical. So typical is 95% of the values around the mean. So that leaves out these very extreme values that are extremely high or extremely low, and that only constitutes 5% of the values, and those values are considered not typical. Okay, so typical we define as being 95% of the values around the mean. So it turns out that some of you guys had very good insight when we first started talking about this binomial probability distribution, and you were able to recognize that half of this distribution will be equal to the other half. I.e. it will be symmetric. So if you plot this distribution here that represents the number of heads observed out of 10 flips. Then we said that, again, what is the most typical number of heads observed out of 10 flips? Yeah, it would be 5. So at 5, you have a bar with a certain height that represents the probability that this variable takes on each of its values. So at 5, you have a bar with a certain height that corresponds to the probability. But we said that even though this is the most typical number, it doesn't mean that you're going to get 5 heads every time you flip a fair coin 10 times. So at 6 heads, there's gonna be a probability of that happening, but it's gonna be less than the probability of observing 5 heads. So as you move away from 5 in either direction, you're gonna have this, the height of this bar, or the probability, is gonna get lower and lower. And same thing for the other direction. So this is the distribution you might see if you convert this distribution from a table into this graph form. And just like we expect, we see that half the probabilities are the same as the other half of the probabilities. This graph is symmetric. And so if you were to approximate the shape of this graph, what do you think it looks like? Yeah, it looks like a bell curve, very good. So because it looks like a bell curve, we can use this bell curve relationship that we've talked about in the past, where if we want 95% of the values around the mean, then for a bell curve specifically, that 95% corresponds to how many standard deviations from the mean. Yeah, very good. So 2. So that 95% is really 2 standard deviations from the mean. So that means that if we want to capture 95% of the values from the mean, we just start from the mean, 5 in this case, and we add 1.5 standard deviations. We add 2 standard deviations to get the upper bound for the extreme value, and we subtract 2 standard deviations in the other direction. So we want the mean plus or minus 2 standard deviations. So the shorthand notation for that, remember the mean, the variable for the mean was this mu symbol, and then plus or minus 2 standard deviations, and the symbol for the population standard deviation, recall, was this Greek letter sigma. So all we have to do to find the typical range of values is to find the mean plus or minus 2 standard deviations. So in this case, the mean is 5, and then plus or minus 2 times 1 standard deviation in this example is what? Yeah, we ended up taking the square root of NPQ, that ended up being 1.58. I approximated that to 1.5. So,
what's the point of approximating it down
oh,
instead of up?
just so that we could get nice whole numbers here.
Okay, gotcha.
Yeah. But this is just to understand it intuitively, what it means to be a standard deviation. So I'm approximating so that you can see the big picture here.
Okay.
But here I'm specifically telling you that I'm approximating. So whenever I want you to approximate, then I'll let you know, or the homework will let you know.
Alright.
Yeah, so here, after we approximated to 1.5, what is the lower bound of this range here? It will be 5 minus 2 times 1.5, which is 2. And then the upper bound will be 5 plus 2 times 1.5, or 5 plus 3, which is 8. So what does this mean? This means that the typical range of values, every time you flip a fair coin 10 times, will be somewhere between 2 and 8. Which means that if it's indeed a fair coin, every time you flip it 10 times, 95% of the time you'll see 2 heads to 8 heads. So that's if it's a fair coin. If it's unfair, if it's not a fair coin, you'll see a number of heads that's outside this range. You'll either see 1 head, or 0 heads, or 9 heads, or 10 heads. That's if it's unfair coin. But if it's fair, then 95% of the time, you flip it 10 times, you'll observe anywhere between 2 heads to 8 heads. You won't necessarily see 5 heads every time just because it's a fair coin. Any questions?